Welcome students. In today's lesson we're just going to talk about a very important concept in physics called conservation of mechanical energy. And in that we're going to talk about what mechanical energy is, we're going to talk about different types of systems, and we're going to talk about how energy is conserved, building upon those previous lessons that we did where we talked about work energy theorem and the different types of energy involved and how energy and work are interrelated. So if you need to do a little bit of review on that, feel free to go back and have a look at that. Okay, so the first thing that we should talk about is we should state what conservation of energy in fact means. Well, it states that energy can neither be created nor destroyed. It can only change from one form to another. So in other words, another way of putting that is that you cannot get energy out of nothing. It would be marvelous if we did. We wouldn't have to be, bleeding the ground dry of all the fossils that are in there, racking our brains to figure out how we can curb greenhouse gases. So this is a really big issue, and if we could in fact conserve energy or make energy out of nothing, then the world would be a very different place. So we cannot, as best we know it, through the physics laws that we know of, it can neither be created nor destroyed. It can just change from one form to another. So very important point that we need to discuss here is we do need to talk about the fact that energy can neither be created nor destroyed. So conservation of mechanical energy, another way of putting it, based on what we already know, is mechanical energy 1 equal to mechanical energy 2, and these are at various different points in time. So the mechanical energy at the beginning is equal to the mechanical energy at the end. Now that could be potential energy at the beginning, and there might be some kinetic energy. Could be potential energy at the end and kinetic energy. In other words, it's a combination of those energies. It is also important to say that the total energy of a closed system will remain constant. So this is what we're talking about here. There's an assumption that it's a closed system. So what does that mean? Well, it means that there is no energy input or output allowed from that system. So is that a very real world scenario? No. But if we look at the universe in general, if we look at the universe itself, that can be seen as a closed system, in which case energy is conserved. Generally, when we look at smaller systems, they tend to be open systems because there is energy lost or gained by the system, and in that case, there's work done to the system or by the system. For example, an open system is when work is done on the object or by the object. When work is done by the object, it may be in the form of friction. If work is done on the object, if I have a ball or something in my hand and I lift that up higher, I give it more energy relative to the ground. It's got a higher potential energy. So I had to do work on the ball, the system, in order for that to happen. So that's a situation where it's an open system. So if we look at a closed system and we look at the little GIF in front of us here, we have a pendulum swinging. Now in this scenario, you'll notice a couple of things. If we look at the pendulum, once it reaches this final point in a second, and we look at the bar graphs over here, we'll see that it is all potential energy. Okay, so we can see that all of that is potential energy. As the pendulum falls at the bottom of the point, it is all kinetic. So it merely goes from potential to kinetic to potential. In other words, from one form to another. And when the pendulum is at the bottom of its swing, it has transferred all of that energy to kinetic energy. In other words, there's no potential at the very bottom. There's no gravitational potential energy because it is at that bottom point, that H equals 0 point. It's at the bottom of its swing. Now you'll also notice that the total energy, so this potential energy in the bar graph, the blue potential energy, which is up here, is equal to the kinetic energy at its highest point. So those values should in fact be equal. If they are not equal, then we're looking at a closed system. Another way to, an open system, sorry. Another way to put that closed system is ME1 is equal to ME2. So you'll see a lot of questions which will talk about that energy being conserved. And you need to break down what is that mechanical energy one. Is it all potential energy? Is there some kinetic energy involved? Is it all kinetic energy? So you really have to have an appreciation for that. Of course, not all systems are closed systems. If there's any friction present, the work done by frictional force is transferred to heat energy as an example. And friction is a non-conservative force. So if you look at our skater slash skier going down the hill, and we look at these wonderful energy bar graphs at the side here, we can see that the skier begins with potential energy. As they go down, the kinetic energy starts increasing, so the total mechanical energy remains constant until they hit this rough patch. When they hit the rough patch, you'll notice the mechanical energy in the green starts dropping. And that is because the total energy of that system is now being reduced. In other words, there's energy leaving that system. If we look at it again, speed is increasing because the kinetic energy is increasing to a maximum at the end, and then when the rough patch is hit, the mechanical energy drops, and you'll notice the yellow part of the work bar graph is increasing. So there's negative work being done on the system, or in other words, there's work being done by the system, okay, as it hits that patch, and that's in the form of frictional forces being done to remove that energy. So a force is non-conservative if the work it does on an object that moves between 2 points depends on the path taken. So it is not conservative if the work that it does depends on the path taken. So all along that path, the work that's being done on it. So in the example that we looked at, the frictional work that was being done to remove energy on the skier, that followed the path taken by the skier. And the work it does on an object that moves through a round trip is non-zero. So in other words, there's work. So a force is non-conservative if there's some work involved. So typical examples would be friction force, normal force, propulsion forces, and so on. A force is conservative if the work it does only depends on the 2 points and not what happens in between. And also if the work that it does on an object is zero. So gravity, force of a spring, and so on, they would be seen as conservative forces, and they would tend to, operate within a closed system paradigm. So a typical example that we could look at, conservation of energy example, would be one like is shown on screen. A 3 kilogram watermelon sits on a table 1.2 meters above the ground. What is its potential energy at the top compared to the ground? What is its kinetic energy at the top? Remembering that for potential energy, we have a pretty tidy little equation for that. The potential energy is equal to mg delta h, and kinetic energy is a half mv squared. Now, if it's not moving at the top, of course, the kinetic energy would be zero. There's no velocity. And the other thing that you might need to find out, or you may be asked, is what is the speed that it will hit the ground at? So that's a very typical type of question. The answers are at the bottom. And that's a very typical question that you would be asked. Let's have a look at another one. You'll also notice that, by the way, that energy is in joules. Another type of problem is a roller coaster car starts from point A to point B, starts at point A, moves to point B. What's the speed at the bottom of point B? Now, I should also say that you may be asked to calculate the speed at various points throughout that fall, in which case, of course, you may have some kinetic energy, some potential energy. So I've actually, in another video, which I will provide a link for on screen, I've solved both of those questions and just done a full tutorial having a look at those. So if you want to look at those, you'll see how to solve those. But today was just about an introduction to closed open systems and that concept of mechanical energy as it relates to conservation of energy.